Before there was a spark, a bang, or even the ticking of a cosmic clock, what was there? Did the universe spring from a cause, or was it born without one? The deeper we look into the origins of everything, the stranger the answers become. In this journey, we'll dive beyond the Big Bang, challenge the very meaning of nothing, and explore whether the universe created itself, or if something else set it all in motion. From cutting-edge physics to speculative models that stretch the limits of imagination, this isn't just a story about the birth of our universe, it's a quest to understand whether there even was a beginning. The paradox of a beginning without a cause. Everything we've ever known has a cause. A spark lights a fire, a push starts a swing, a thought triggers a word. But when it comes to the universe itself, we hit a paradox. What caused the very first cause? If the universe had a beginning, what came before it to trigger that event? And if nothing came before, how did something begin without anything to start it? This is the problem of causality at the edge of time. In our daily lives, the concept of a start requires a starter. But if time itself began with the universe, then the very notion of a before becomes meaningless. That's what makes the origin of the cosmos so deeply unsettling and so fascinating. If the universe is a chain of dominoes, we've found the first one, but there's no hand in sight. In classical terms, a beginning demands a cause, but in quantum mechanics, randomness rules. Events can happen spontaneously, without an outside trigger, governed only by probability. Could the birth of the universe be one such event, a colossal quantum roll of the dice? Time before time, is before even a real question? To ask what came before the universe is to fall into a linguistic trap, one built into our biology, our brains, and the very structure of human thought. But what if before simply doesn't exist outside the framework of time? What if time itself was born in the same cosmic flash as matter, space, and energy? According to Einstein's theory of general relativity, time is not some absolute ticking clock that ticks whether anything exists or not. Time is a dimension, woven into the fabric of space itself. So when space began, time did too. Asking what came before the Big Bang, then, is like asking what's north of the North Pole. The question collapses under its own logic. This isn't just an idea. In physics, some ideas, like Stephen Hawking's no-boundary theory, say the universe started out in a state that had no past, present, or future. It was ruled by the rules of quantum mechanics. In this picture, the early universe didn't just pop into being, it existed in a strange, timeless state, until it changed into something that had time. When we ask, what happened before the universe? Maybe we're asking a question that doesn't have a good answer. It's possible that there is no before, because time as we know it already existed. The illusion of time. Does time have an edge? We think of time as an arrow that shoots from the past through the present and onto the future. But what if this line is just a trick? What if time doesn't flow at all? What if it's something static, like a layer of space? What if time is always there, even if we only experience it in slices? Before we can really think about whether the world could make itself, we need to break down our most ingrained belief, that time is basic and linear. That old Newtonian model of how things work was thrown off by modern physics, especially Einstein's theory of relativity. Time can change in relativity. There are forces acting on it that cause it to bend, stretch, and twist. Near a black hole, time moves more slowly. On top of a peak, it goes faster than at sea level. If time is relative, how can it be the fixed point where everything starts? Then there's the concept of the block universe. According to this idea, past, present, and future all coexist. Time isn't something that flows, it's a landscape. We, as conscious beings, move through it like a spotlight scanning a frozen film reel. Every event that ever happened and ever will exists at once. From this perspective, asking when the universe began is like asking which frame of a movie is real. They all are. The difference is only one of perception. Quantum physics makes things even stranger. Time doesn't show up at all in the Wheeler-DeWitt equation and some other theories. At its most basic level, the world has never changed. Where did time come from? Some scientists say it's an emergent property, like how warmth comes from molecules moving. To put it another way, time might not be built into the universe itself. Instead, it might come from the connections between events and particles. It's just a trick of the mind that things are changing. As it turns out, there is no need for a first moment if time is not important. There is no clock to start. There is no zero on the cosmic clock. This has very important implications for how the world came to be. If cause and effect are part of emergent time, then a world that makes itself doesn't need a reason. If time doesn't start until after the world was created, then the question of what came before time has no point. We evolved to understand cause and sequence. Fire leads to smoke. Birth leads to death. So we instinctively demand that the universe too must have come from somewhere, caused by something. But maybe this is a trick of perception. Maybe the universe didn't begin in time. It began with time. What if the universe had no beginning at all? At first, the question seems silly. How can something exist if it has no beginning? We know a lot of things because they began somewhere. Trees grow from seeds. People are born. After eons of falling apart, even stars light up again. It makes sense to wonder, when did this all begin? When we look up at the universe. Did it start? Might be a better question though. Some physicists and cosmologists argue that the universe might be eternal. No beginning, no end. Just an infinite, self-existing structure. This idea turns our concept of origin on its head. In a timeless or cyclic universe, the Big Bang might not have been the beginning at all, but merely a dramatic event in an ongoing cosmic cycle. In this scenario, asking what caused the Big Bang is like asking what caused the sunrise. It's part of a pattern, not a one-time event. The most basic version of this idea is called the steady-state theory, once a rival to the Big Bang. It suggested the universe has always existed as it is now, with new matter continuously forming to maintain its average density despite expansion. The theory fell out of favour after the discovery of cosmic microwave background radiation, the afterglow of a hotter, denser past. Still, it planted a provocative seed. What if the universe doesn't need a beginning? Newer forms of this idea are based on more up-to-date science. For example, the cycle model says that the universe is always getting bigger and smaller, like a universal heartbeat. It's not a starting with each Big Bang. It's a bounce from the last decline. There is no beginning, nothing but motion forever. Quantum physics is another way to look at things. There are some answers to the equations of general relativity that lead to a world that has been around for a very long time. There was never a singularity in this universe, so there is no edge or first point. The universe may not have started from a point of no return. Instead, it may have always been in a quantum state, only later moving into a classical growth phase that looks like the universe we can see. Even more radical is the idea that beginning itself is a flawed concept, a relic of our intuition shaped by life in a world with finite events and lifespans. If time is not fundamental and space-time itself is emergent, then the whole concept of a start becomes meaningless. The universe might not have begun in the way a story begins. It might just be. This eternal universe isn't some lazy cop-out to avoid the hard questions. On the contrary, it's an answer that arises naturally from some of our best current theories. Loop quantum gravity, certain models of string theory, and the Hartley-Hawking no-boundary proposal all allow for universes without an initial moment. They suggest the cosmos doesn't need a push to get going. It simply exists, governed by laws that don't require a kickoff. Virtual particles and the quantum vacuum. creation from empty. What's left when you take away all the planets, all the stars, and even the tiniest atoms? You might say nothing. Nothing, a perfect void of silence. In quantum physics, however, nothing is not empty at all. It's a boiling, buzzing froth of activity full of ghostly particles that appear and disappear in the blink of an eye. Hello and welcome to the strange world of the quantum void. At the smallest scales of nature, the domain of quantum mechanics, energy never sits still. Even in a region of space where there are no real particles, quantum uncertainty causes fluctuations in energy. These fluctuations give rise to virtual particles, pairs of particles and antiparticles that pop into existence for a fraction of a second, then annihilate each other before the universe even has time to notice. They can't be directly observed, but their effects are very real. You might be thinking why these particles are important if they are going to be gone so soon. There is no doubt that the answer is yes. The Casimir effect is a real effect that happens when two metal plates are in a vacuum and seem to be pulled together by the nothing between them. Virtual particles help make this effect possible. That's the work of virtual particles. They also help explain Hawking radiation, which is when black holes lose mass slowly over time because of changes in quantum mechanics at their front ends. But here's where things get wild. If space can spontaneously produce these particle pairs, could the entire universe have emerged in a similar way? Some physicists, like Edward Tryon, have proposed just that. His idea, first presented in the 1970s, was bold and simple. Maybe the universe is just one of those things that happens from time to time. This point of view says that the world is a huge quantum fluctuation. If you wait long enough, the rules of probability in quantum physics let strange, once-in-a-trillion events happen. A universe like ours could be the most unlikely thing that could happen. It could briefly get energy from the void and inflate into a full-fledged universe. The main flaw in this argument is that the universe may have no energy at all, with positive energy from matter and radiation equaling negative gravity energy. With the growth of quantum cosmology, this idea of a universe from nothing got even more support. The idea behind these models is that space-time is a quantum system that can tunnel from nothing to being. But once more, nothing doesn't mean a clean start. A quantum vacuum is one that is unpredictable, changes all the time, and is controlled by physical rules. The laws do the work, not an aware being or a holy finger. Of course, this still leaves us with another big question. Where did the laws of physics themselves come from? Even if a quantum vacuum can birth universes, it needs rules to follow. And rules imply structure. That's the frontier where quantum cosmology meets metaphysics. Because even if we accept that universes can arise from quantum vacuums, it doesn't fully solve the problem of ultimate origin. It just moves it one step back. Still, the idea that nothingness is fragile and can blow up into something as huge as the universe is one of the most amazing things that modern science has shown us. It changes the way we think about creation, not as a miracle, but as something that will happen by chance if enough time and conditions are right. The role of entropy. Can something rise from disorder? If there's one law in physics that almost everyone has heard of, it's the second law of thermodynamics. It's the one that says entropy, the measure of disorder in a system, always increases over time. You spill coffee and it spreads. Ice melts, stars burn out, order decays. But what if the story doesn't end with chaos? What if entropy is not the enemy of creation, but a key player in it? Let's take a closer look at this paradox. The second law seems to scream that the universe is destined for disorder. But at the same time, we live in an exquisitely structured cosmos. Galaxies spin in elegant spirals. Stars light up in balanced fusion. DNA molecules self-assemble into intricate blueprints of life. How can increasing disorder lead to so much visible order? To find the answer, we need to know what entropy really means and how it acts in a world that is expanding. Entropy isn't just about how messy things are, it tells you how many different ways there are to arrange the parts of a system. When there is a hot, uniform fog, the particles move around randomly. This is called high entropy. But in the early universe, right after the Big Bang, if there was one, everything was very smooth and regular. This is called a state of very low entropy. So how does a low entropy universe give rise to stars, planets, and people? Because gravitational systems don't behave like your bedroom or a gas in a box. In fact, as gravity does its work, it clumps matter together, forming structures like stars and galaxies. And here's the twist. In doing so, the entropy of the overall system increases. The stars and galaxies represent local decreases in entropy, but they generate vast amounts of heat and radiation, pushing the total entropy of the universe higher. On every level, this process takes place. Even life, which is the perfect example of order and complexity, doesn't go against entropy. It follows it. Things that are alive create and release entropy. They take in ordered matter, like food, and give off disorder, like heat and waste. Evolution doesn't go against the second law. Instead, it works with it, using energy differences, like the sun's heat on Earth, to help self-organizing systems form. Some physicists have proposed that entropy gradients could be the very reason time flows in one direction. That arrow of time, always pointing forward, is a result of entropy increasing. And some bold theories suggest that the universe began in a highly ordered state, not by chance, but because a low entropy state was the only one stable enough to expand. In other words, order didn't come after the beginning. It was the beginning. In cosmology, there is also an interesting thought that our universe could be one side of a time-symmetric universe. On the other side of the Big Bang, there is a mirror universe where entropy also rises, but in the opposite way of time. If this is true, our orderly start could be part of a bigger cosmic balance in which chaos is built into the very structure of the universe. Yes, entropy makes sure that things like heat will spread, coffee will spill, and stars will die. On the other hand, it makes room for structure to grow, complexity to appear, and even time to move. Without a doubt, the world may have formed because of chaos rather than in spite of it. Was there ever truly nothing? Imagine for a moment a complete absence of everything. No light, no matter, no energy, no space, not even time. Just pure, absolute nothingness. Now try to hold that image in your mind. It's almost impossible, isn't it? Because every time we imagine nothing, we tend to smuggle something in. A black void, an empty room, a space waiting to be filled. But those are still somethings. This leads us to one of the most controversial and mind-bending questions in modern cosmology. Was there ever truly nothing? At first glance, this may look like a religious or philosophical question, but in the last few decades, it has become an important area of scientific study. Scientists study the universe and physics to try to figure out what nothing really means, and if it ever existed. We have to ask, what do scientists mean when they talk about nothing? In quantum physics, the vacuum of space isn't empty. It's seized with invisible energy. Particles pop in and out of existence in a quantum froth that's anything but tranquil. This so-called quantum vacuum is often described as nothing, but clearly it's something. It has properties. It fluctuates. It has a structure governed by the laws of physics. In fact, some theories, like those involving quantum field theory, suggest that even in the absence of particles or photons, space still contains fields. These fields can be excited to produce particles, which leads to the bizarre idea that nothing can give rise to something through natural processes. But again, this nothing is more like a stage with the lights turned off. It still exists. It still obeys rules. What about really nothing? There are no rules, no dimensions, and no quantum changes. Is there really that kind of nothing? This is where things get rough. Lawrence Krauss and other scientists say that the universe could have formed from nothing because quantum physics allows for this to happen. But critics are quick to point out that this nothing still rests on a framework that is already there, like the rules of probability or the basic ideas of quantum physics. No, that's not the kind of nothing that the question is asking about. In fact, it may be impossible for absolute nothing to exist or to have ever existed at all. Why? Because if absolute nothing truly existed, it would remain nothing forever. There would be no potential, no instability, no hidden spark to give rise to something else. So for something to emerge, there had to be at least some kind of substrate, even if it was so simple and strange that it doesn't resemble anything we're familiar with. In this sense, perhaps nothing is unstable by default, not a void, but a waiting state. Another extreme idea is that nothing is just a word that people have made up using language and comparison. Because of how our brains are wired, we think of nothing as the opposite of something. We think in terms of light and dark, sound and silence, presence and non-existence. But maybe there isn't a choice between those two in the deep structure of reality. What we think of as nothing could just be a mental image of something we don't fully understand yet. The problem with nothing: philosophers versus physicists. To a scholar, nothing must mean that there is nothing at all. This means there is no time, place, possibility, or properties. Lack of anything. It's no longer true nothing if you can explain it, picture it, or give it any traits at all. This is why many philosophers, including Parmenides, Heidegger, and Sartre, have said that nothing is not only hard to understand, but it might also not make sense. What can we say about what is not that doesn't turn into what is? And yet, physicists like Stephen Hawking and Lawrence Krauss have repeatedly claimed that the universe can and did arise from nothing. Krauss even titled his book A Universe from Nothing, arguing that quantum fluctuations in empty space, governed by the laws of physics, can produce matter, energy, and even space-time itself. But to philosophers, that's a bait and switch. That nothing is full of laws, fields, and fluctuations. It's not the deep nothing of metaphysics. It's a something in disguise. This raises a crucial question. When scientists say nothing, what do they really mean? A lot of the time, they mean the quantum vacuum, which is a state with no particles but lots of potential because of quantum fields. They could also be talking about a state with very little entropy or symmetry, which makes it easy for symmetry to break on its own, which can cause matter and energy to appear. These are real ideas in physics that can be tested and are based on math. For a philosopher, though, these meanings avoid the main point. It's not nothing if your nothing has rules, limits, or changes. Here lies the fundamental divide. Physicists prioritize what can be measured. Philosophers prioritize what can be reasoned. To a physicist, the question, why is there something rather than nothing, is meaningful only if the concept of nothing can be defined within the boundaries of a physical framework. Otherwise, it's metaphysical speculation, interesting maybe, but outside the scope of empirical science. To a philosopher, the same question is the most important question of all. Why is there anything instead of an eternal, unchanging void? What allowed something to be possible in the first place? And so, we return to the question, is nothing even possible? Maybe not. There might have been something there all along, just in a different form. Maybe the nothing that scientists talk about is the closest thing that reality lets us get. Or, as some thinkers say, nothing might just be another illusion and void we made up to make sense of the present moment. Infinite regression. Who created the creator? Picture a kid asking, who made the universe? In response, God did. Then the obvious question follows, okay, but who made God? Infinite regression is a logical mess where causes keep chasing each other backwards forever. As you give answers, the question moves backwards by one step. Something must have started the first cause. Then what did the first cause start? Furthermore, if the first cause had a cause, what was that cause? This isn't just a clever riddle, it's a deep problem for any theory, scientific, theological, or philosophical, that tries to explain the ultimate origin of everything. The concept of sufficient reason is a good place to start. It's the thought that everything needs to have a reason for being. We naturally want to know why things happen, whether it's a star, a tiny particle, or the whole universe. But if the line of events goes back forever, we never get a complete answer. We only get a never-ending list of questions that need to be answered. Many theories, especially traditional theistic ones, use an uncaused cause to get around this. It was known as the prime mover by Aristotle. It was what Aquinas called God. The idea is that there must be a supreme being or principle that doesn't need to be explained. Something that just is, without a reason, timeless and necessary. But modern thinkers challenge this logic. Why must the first thing be a mind or deity? Why not a quantum fluctuation, a timeless law, or a loop of self-causing events? In quantum physics, it's hard to tell what causes what. Small-scale events don't always happen in neat chains of cause and effect. Particles can appear out of thin air for no clear reason. Could the world have done the same thing? Some physicists speculate that the universe is causally closed, a self-contained loop where time and cause curve back on themselves. In these models, the universe doesn't need an outside cause because its beginning and end are linked. It's like asking who created the circle. It's a closed shape. There's no starting point that needs a creator. The question is still strong though. What made it possible for the world to make itself? Where did the rules of physics and quantum mechanics come from if they shaped everything else? Are we just moving the problem up a level to a meta-universe or a more complex mathematical world? There's also a possibility that our need for causes is a limitation of the human mind. Maybe not all realities require causes the way apples require trees. Maybe the first cause isn't a thing at all, but a boundary, a transition, a change in state. And so, we're left with a paradox. If everything has a cause, then there must be an infinite chain, or something that caused itself. If something caused itself, how could that even work? And if something has no cause, why should that stop at just one thing? Was there ever truly nothing? What do you picture when you hear the word nothing? Is it pitch black emptiness? A void without stars, planets, or people? That image might feel intuitively right, but according to modern physics and cosmology, it's far from accurate. In fact, it might be completely wrong. Nothing isn't as empty as it seems in the world of science. First, let's talk about quantum physics. There is still energy in a vacuum, which is a place with no matter in it. It is full of quantum changes and crackles with potential. These changes can make and destroy particles on their own, like bubbles popping in and out of existence in a pot of hot water. So even the emptiest as space isn't really empty. It's full of possibilities. Physicists call this the quantum vacuum, and it's not just a theoretical idea. We can observe its effects. The Casimir effect, for example, is a measurable force between two metal plates in a vacuum, caused by quantum fluctuations of empty space. It's a haunting reminder that even the void has substance. It gets even stranger from here on out. Some ideas say that this kind of quantum nothing may be where the world came from. It is possible for a void to sprout a whole universe if it is unstable enough. This would happen in a way similar to how quantum fluctuations happen. From a quantum point of view, the world might have no energy at all, so it wouldn't be against the rules of physics. In a way that looks like a cosmic accounting trick, negative gravity energy could balance out positive matter energy. Stephen Hawking once said, because there is a law such as gravity, the universe can and will create itself from nothing. But critics, especially philosophers, have pointed out that what Hawking calls nothing is actually something, a framework of physical laws, a quantum field, a space-time stage. So was there ever true nothing? That depends on how we define it. To a philosopher, nothing means the absence of everything. No space, no time, no laws of physics, no quantum fields, not even potential. Just nothing. But here's the catch. We have never observed such a state, and we don't know if it can even exist. It's not just that we've never seen nothing, it's that we might not be able to. The idea of nothing might not exist in the real world, but only in our words. We think the universe has always been something, even before there were stars, light, or matter. Energies, dimensions coiled up into knots, or an unknown first nature may have been there. And here's another twist. If nothing can give rise to something, is it really nothing anymore? This leads to a deep paradox. If we say the universe came from nothing, we must define what that nothing was. But if it had properties, like instability, potential, or laws, then it wasn't truly nothing at all. Laws without lawmakers. Can physics exist without space? We often imagine the universe as a grand machine, its gears turning according to the laws of physics, gravity, electromagnetism, quantum fields. But here's a wild question. Do those laws require a stage to act upon? In other words, can physical laws exist without space itself? At first glance, the idea seems absurd. After all, how can gravity pull without space to curve? How can particles move without a distance to cross? We tend to picture laws of physics operating in space. But what if that gets it backward? What if the laws generate space rather than reside within it? This flips our intuitive thinking. Instead of imagining a universe that begins with space and then fills it with rules, imagine the rules coming first and space being born from them. Here you are in the world of pre-geometric physics, where scientists look into models that don't take space or time as basic. One way to do this is through causal dynamical triangulations, CDT, which builds space-time out of small, separate pieces, like Lego bricks. The blocks are space, they are not in space. When seen on a big scale, their order follows simple rules that make sense in terms of Einstein's general theory of relativity. In this framework, space and time aren't background features, they're emergent. They're like temperature in a room, not a thing you can isolate, but a pattern that arises when lots of particles behave a certain way. The computational world theory by Stephen Wolfram is even less concrete. He thinks that reality is like a cosmic cellular automaton. It's made up of a huge computer program with rules. The building isn't built into a place that was already there. Space and time are not things that we see or touch. Instead, they are the connections between pieces of knowledge. In the beginning, there is no where, only links. This means that the rules are no longer valid, right? What's the next big logical question? Can these rules exist if there's nothing for them to govern? Some physicists say that laws are mathematical facts that don't depend on space, matter, or even the world itself. For example, they say that 2 + 2 = 4. If that's the case, nothing is to blame. They're just true. Always have been. It always has been. This echoes Max Tegmark's mathematical universe hypothesis, which suggests that the universe is a mathematical structure. We don't discover laws, we inhabit them. But this leads to a deep tension. If laws exist timelessly and don't need space, then what gives them physical reality? Why does a specific set of rules, like our laws of physics, govern the universe instead of others? Why these rules and not countless alternatives? We're not sure. That's part of the puzzle. Cause and effect are hard to understand when there is no room between them. There is no shift or separation, no before or after. In this kind of world, the idea of a law starts to look like something else, like a vague, pure truth that is about to come out. But what about physics without space? Self-creating universes in loop quantum gravity. Think about a universe that just exists on its own, with no gods, multiverse builders, or cosmic clockmakers. Just rules that keep going around and around, creating a universe from itself. It's not science fiction. It's one of the wackiest but most important ideas in modern physics. It comes from loop quantum gravity, LQG. To grasp it, we first need to understand the problem that loop quantum gravity is trying to solve. General relativity, Einstein's magnum opus, explains gravity as the bending of space and time. Quantum mechanics, meanwhile, governs the bizarre behavior of subatomic particles. But when you try to combine the two, things break down, especially at singularities, like the one believed to exist at the beginning of the universe. This is where loop quantum gravity comes in. The idea is that space is not one continuous line, but rather is made up of small, unbreakable pieces, like the atoms that make up space itself. These pieces, or loops, are so small that they're like the Planck length, which is about 10 to the minus meters. Smooth spacetime breaks apart at this size into a quantum fabric, which is a foam of separate loops. What does this mean about how the world began? In other words, the Big Bang might not have been the start at all. Loop quantum cosmology, which grew out of LQG, says that there was a big bounce before the Big Bang. The universe didn't just appear out of thin air, it expanded after shrinking. As the older universe shrunk, the density rose, but it didn't collapse into a singularity because of quantum gravity. These impacts worked like a pushback, stopping the fall and starting a bounce. The universe didn't start in this model, it went through cycles. Even more interesting is the fact that this bounce isn't just a silent return. Some forms of the theory say that the quantum shape of spacetime can change on its own and make its own conditions. In LQG, the loops don't need a place that already exists. They make space by interacting with each other. To put it another way, the world might be making itself. The word doesn't mean magic, but it does mean math. The catch is that time also comes from these quantum events, so there was no before the world in the usual sense. Time might not move from the past to the future. Instead, it could come from a chain of quantum events that don't need a starting point. If loop quantum gravity is right, then the universe didn't explode into being from absolute nothingness. It evolved from a quantum structure that had no classical time or space. The loops wove together a tapestry we now call space-time, and from that everything else unfurled: stars, planets, life. It's still just a guess, but it can be tested. Using cosmic microwave background radiation in experiments might show signs of the bounce. If proven, it would change the story of how the universe came to be, not as a singularity, but as a turning point in a much bigger cycle. Loop quantum gravity says that the answer to the question, did the universe create itself, is yes, in circles, without a start and no end. Causal, set theory, when events make reality. How would you feel if space and time weren't smooth and continuous like a river, but more like a jumbled mess of moments that could be counted? This is the big idea behind causal set theory, a model of space-time that could not only explain gravity, but also change the way we think about what the world is made of. Causal set theory, CST, starts with a deep question. What is the essence of space-time? Instead of treating it as a smooth fabric that curves and stretches, CST treats spacetime as a series of discrete elements called events. These are not particles or even locations, but individual points in spacetime, each connected to others by cause and effect relationships. Think of reality as a vast, ever-expanding family tree, not of people, but of events. Each new event is born from others that came before, linked by causality. Just like a family tree maps parent to child relations, the causal set maps which events can influence which. This lattice of causal relationships, not the familiar 3D space, becomes the foundation of reality. Space, time, and even the rules of physics may be able to be figured out from this simple arrangement of points and the links between them. The beauty of this idea comes in how simple it is. You don't need time or room to begin with. You just need a list of events and the links between them. How far apart are the two events? That's just the number of steps in the chain of events. How much time has passed? The order in which things happen. How does the shape of space work? A feature that appears based on how closely these direct links are grouped together. In CST, the universe doesn't evolve through time, it builds time. This might sound abstract, but there's a deep purpose behind this model. Like loop quantum gravity, causal set theory is one of the few serious attempts to create a quantum theory of gravity, something that unites Einstein's general relativity with quantum mechanics. CST's big claim is that if you make space-time discrete, you can dodge the infinities and singularities that plague standard models. The theory says that because events can be counted and are caused in a certain order, the universe grows like a living thing, with new elements being created in a set order that is controlled by quantum rules. Sequential growth dynamics is the idea that comes from this. This idea says that the world is growing one moment at a time through causal connections. Space and time are not just there, they are always being made. As you keep thinking this way, you come to a shocking conclusion. The world is making itself. Not all at once. It's not from the Big Bang, but little by little, one event at a time, like a cosmic book filling in its pages. Causal set theory is still highly theoretical and unproven, but it offers a fresh and compelling lens for understanding the cosmos, not as a vast balloon expanding in space, but as a network of events unfolding according to the rules of causality. With time and space as illusions, we infer from the links. The universe as a quantum fluctuation. It's hard to imagine being in a place that has no space, time, matter, or even light. A place that is so empty it's hard to understand. Still, something sparks into being from this nothingness. There is a birth. No hand from God, no thought to guide you. Nothing more than a chance twitch in the quantum fabric of nothing? This is the amazing idea behind the idea that the world is made up of quantum fluctuations. The quantum vacuum is the tiniest level of space, much smaller than atoms, molecules, or even protons. It is a sea of doubt and possibility. Most of the time, empty things are not empty. This is because it is full of particles and antiparticles that come and go all the time. This crazy behavior is real. It has been seen in labs with effects like the Casimir effect and virtual particles in quantum electrodynamics. Even in a vacuum, the quantum world is full of changes that can't be stopped. Because of quantum uncertainty, small bits can appear out of nowhere. So why can't whole universes? Physicists like Edward Tryon promoted this line of thinking in the 1970s. They said that the universe itself might be the ultimate free lunch, a quantum fluctuation so big that it created everything we know. This idea says that the negative energy of gravity properly balances the positive energy of matter. This means that the universe has no energy at all. In the end, nothing was lost and everything came from nothing. But how could something that changes so much make a world with time, space, and physics laws? This is where things get more complicated. Changes in the quantum world don't just make random particles, they also make probability clouds. These clouds show how likely it is that certain things will happen. If there is no time or endless time, there will always be a change that is big enough and organized enough to create a bubble of space-time that grows, changes, and expands. Sound familiar? That's the inflationary model of the Big Bang. Physicist Alan Guth proposed that our universe went through an unimaginably rapid expansion shortly after it popped into existence. Quantum fluctuation plus inflation equals cosmos, and once this baby universe inflates, its own internal rules take over. Gravity, electromagnetism, nuclear forces, all these may freeze out of the high-energy chaos as the universe cools, setting the stage for atoms, stars, planets, and life. The interesting part is that if one world can come from a blip, then why not many? Some models say that new worlds are constantly popping up, and each one has a few small differences. Our world is just one lucky draw out of a huge number of them, and each one has its own version of reality. Most fall apart right away. Some, like ours, stay the same and grow. Some people who disagree with the quantum fluctuation theory say that it depends too much on physics rules that didn't exist before the universe. In the end, how can quantum changes happen if there is no time or place for them to happen in? That's a good question, but in many ways of understanding quantum physics, time and space are not basic properties, but rather qualities that appear. In this case, the fluctuation might have been the first bit of time and the first point in space. Creating a world from a hiccup in the void is a crazy idea. There is no plan, not planning to. Life is just a game of chance, with the dice being rolled all the time. Baby universes in the multiverse nursery. The multiverse, the idea that there are many, maybe even endless worlds, is at the heart of this theory. You should know that these are not just faraway stars and galaxies in our own universe. They are completely different worlds with their own space, time, physics rules, and even dimensions. It's possible that these worlds are constantly forming in a way similar to how stars are born in stellar nurseries. How then do baby universes come to be? Quantum tunneling and inflation are linked to one possible process. Random changes can make bubbles form in high-energy quantum fields, like the ones that were thought to exist when the universe was first formed. When things are just right, these bubbles can quickly grow into self-contained areas of space-time, which are called baby universes. Inside each bubble, inflation keeps going, making it possible for galaxies, matter, and energy to form. A baby universe might look like a small area of bent geometry in a parent universe, a bump or knot in the fabric of space-time from the outside. But from the inside, it would look like a full-fledged universe with no signs of any other universes around it. The crazy part is that these little worlds may be forming all the time. According to the idea of everlasting inflation, which is based on the idea of normal inflationary cosmology, inflation never stops fully. Inflation only stops in small areas, like our universe, where it forms isolated bubbles of regular space-time. It keeps going everywhere else. This creates a structure that keeps spreading out, a tree of worlds that keeps growing. It's an endless pattern of births in the universe. Some physicists even suggest that black holes might be involved in the process. According to one hypothesis, the singularities at the centers of black holes could be gateways to baby universes. The idea is that matter crushed into a singularity doesn't just vanish, it transitions into a new universe, disconnected from our own. This would mean that every black hole in our universe could be the seed of another cosmos. Imagine that, a universe creating others through its own gravitational collapse, like a cosmic family tree with endless generational branching. Some people think that the multiverse and this baby universe situation in particular can explain the fine-tuning problem, which is one of the biggest puzzles in cosmology. The physical factors in our world seem to be perfectly matched so that life can exist. Stars fall apart too fast when there is too much gravity. They never form if there is too little. It's not a surprise that at least one of the many worlds would have the right conditions for life if they all have different rules. That's the one we're in right now. Still, there are a lot of problems with the baby world idea. One of the most important is that we can't directly see other worlds. They are not linked to ours in a way that makes sense, which means that no signal or information can go from us to them. So the question is, can science ever prove that they exist, or are we just chasing spiritual shadows? Hawking's no-boundary proposal, a universe with no edge. Picture yourself walking on the Earth's surface. From one end of the edge to the other, across countries and oceans, you can move in any direction and never fall off. Why? The Earth's surface is curvy and ends at some point, but it doesn't have any edges. This simple idea was taken by Stephen Hawking and made much bigger, to the whole universe. In the 1980s, alongside physicist James Hartley, Hawking introduced what's now called the no-boundary proposal. At its core, it suggests that the universe, in its earliest moments, didn't begin at a sharp point in time or space. There was no singularity, no edge, and no definitive starting line. Instead, time and space curved gently into existence, like the rounded south pole of the Earth. This model doesn't show any limits on the universe in the past, so there isn't a need for a cause in the usual sense. There was never a time before the universe, because time began in this rounded shape. Hawking and Hartley used complicated math that mixed quantum physics and general relativity to show this. They said that you wouldn't find a random point of infinite density if you went back in time to the beginning of the universe, even beyond Planck time, which is the smallest unit that can be measured. You instead go to a place where time acts more like space. There is no longer a difference between time and space at these points. This period is governed not by classical physics, but by Euclidean quantum gravity, a theory where time takes on imaginary values, as in complex numbers, helping smooth out the equations and eliminate singularities. In this realm, there's no time as we understand it, no seconds ticking by, no cause and effect chains, just a smooth, curved landscape from which our familiar universe gradually arises. Why does this matter then? With the no-boundary proposal, we don't have to ask what came before the universe, because Hawking says that's like asking what's north of the North Pole. There is no answer to the question, not because it is stupid, but because nature doesn't give one. Time is something that happens in the world, not something that exists on its own. So there was no before. This point of view changes the whole argument about when everything began. In this case, there is no singularity that bursts into existence. Instead, the universe forms slowly, following a natural path from a quantum state to the growing space-time we live in now. The theory is beautiful and makes sense theoretically, but it's very hard to test. As of now, we don't have a clear way to observe or disprove it, because it talks about times and spaces that can't be measured. There is a lot of quantum uncertainty in the early universe, and models like this are right on the edge of what science and speculation can say about it. Still, it's one of the most beautiful solutions to the age-old question, where did everything come from? Vilenkin's tunneling from nothing. Probability creates the cosmos. What if the universe didn't need a reason at all? What if it only needed a chance? Alexander Vilenkin's tunneling from nothing idea is one of the most interesting attempts to solve the most important question in the world. How did everything come from nothing? We see rules in quantum physics that are incredibly different from what we see every day. Particles can appear and disappear on their own in a vacuum because of one of those rules. This is not magic. It's a real effect called quantum tunneling that lets particles cross energy obstacles they shouldn't be able to. This is how the particles inside radioactive atoms get out. That's how the sun shines. His theory says that the universe could have come from a quantum vacuum, which is not a place full of gas or dust, but a place where there is no space, time, or matter at all. Not a single thing. Nothing, in this case, means there is no room to move through, no time to measure, and no particles to bump into each other. Just an empty space with no rules. Still, out of this nothingness, a tiny change could appear on its own, based only on quantum chance. It would quickly grow into the huge universe we see today. This is not a guess. It is a formula that is built into the rules of general relativity and quantum physics. The process is often illustrated using the metaphor of a quantum bubble. Inside this bubble is the infant universe. Outside is the realm of nothing. Through quantum tunneling, the bubble pops into being. The laws of quantum physics don't forbid it. In fact, they make it inevitable, given enough non-time. And here's where Vilenkin's contribution shines. He created a mathematical model to describe this process. It predicts that the probability of tunneling is highest for universes with the smallest possible initial size, which then inflate due to their own internal energy, a process closely aligned with cosmic inflation theory. This idea is more than just abstract writing. It has a direct link to things we can see in the universe. The universe is flat, uniform, and very big. These properties match the type of fast inflation that would happen after quantum tunneling from a very small starting point. But of course, that brings up new questions. If there was nothing to begin with, where do the laws of physics come from? What made the rules that the universe followed after it came into being, even if it did? Vilenkin's theory gives a subtle answer to this. It's possible that the rules of physics aren't caused in the usual sense. Instead, they may appear as part of the tunneling event, like a particle spin that wasn't set in motion, but just is. If you look at it this way, rules are just possible results, not conditions that were already there. Some people disagree with the theory because they say it changes nothing into something, like a state controlled by mathematical chance. Vilenkin, on the other hand, says that the world didn't need time, space, or a god to start. It only needed the possibility that is hidden in quantum doubt. When you look at the stars the next time, keep this in mind. They may not have been built or planned, but rather they were made possible. And in the huge roll of the quantum dice, something had to happen at some point. Is the universe a closed causal loop? Just picture a book that can write itself, not because someone wrote it, but because the first page makes the last page happen, and the last page makes the first page happen. The loop ends. It's always been there, the story. Change the book to the universe now. This is what the idea of a closed causal loop is based on. It's the bold idea that the world may have created itself. At first look, it sounds like a riddle or something out of science fiction. How does something become real? That sounds like pulling yourself up by your shoelaces. Today, however, theoretical physics is very strange, especially quantum cosmology and general relativity. A closed causal loop may not just be a psychological idea, it may also be mathematically possible. One of the strangest effects of Einstein's general theory of relativity is that space-time can bend so much that it forms a closed loop in time. This idea is based on this effect. This kind of curve is known as a closed time-like curve, CTC. Anything could go back in time in this kind of loop. The interesting thing is that in these models, the object doesn't break causality. It follows it, since every action it takes was always part of the loop. If the universe contains or is a closed time-like curve, then its beginning is causally linked to its end, and vice versa. In this setup, the origin of the universe isn't a singular start, but rather a cyclical point where cause and effect wrap around each other like a Mobius strip. Some theorists, like Kurt Gödel, have explored universes with these properties. Gödel's solutions to Einstein's equations allowed for time loops under specific rotating conditions. Others, like Julian Barber, argue that time itself might be an emergent illusion, and the idea of a beginning is simply a misinterpretation of a much deeper symmetry in the laws of physics. In a world with a closed causal loop, there is no outside maker, and no point in time where everything began. Existence is instead kept going by its own internal consistency. All things happen because of and because they are caused by other things. It's like a song that's been carefully looped to play over and over again, with no real beginning or end. But there are some problems with this model. The grandfather paradox is the most well known. If something in the loop goes wrong or changes, the whole sequence could fall apart. But the Novikov self-consistency principle in physics gets around this problem. It says that events on a closed loop can't be changed because of how the loop is structured. This gets rid of the paradoxes and inconsistencies that people often worry about in time travel tests. But people who don't believe in cause loops say that they can only explain how the world works, not why it exists. They may avoid having to start, but they don't say why the loop appears in the first place. Others say this point of view can't be proven wrong and is just a guess, more of a mathematics curiosity than a testable theory. The idea still stands though because it's beautiful. There is no need for a cosmic builder, no single point. Don't use endless return. There is only one world and it has always existed. It is a dance of cause and effect that will never end. Mathematical Platonism. Do equations create reality? What if math wasn't just the rules of the universe, but the universe itself? This is the crazy idea behind mathematical Platonism, a philosophical and scientific view that says math systems are reality and not just descriptions of it. In this view, the world exists since there is math. Not figuratively, but really. It may sound abstract, but this idea is taken seriously by many physicists and mathematicians. To understand why, we need to look at the strange and almost magical way math has repeatedly predicted truths about the universe long before we ever observed them. The orbit of planets, the curvature of space-time, the behavior of quantum particles, they all follow mathematical patterns that seem to exist outside of human invention. Physicist Max Tegmark took this idea to its extreme in what he calls the mathematical universe hypothesis, AIM-UH. In his view, every structure that can be described by mathematics exists as its own physical reality. That means not just our universe, but all possible mathematically consistent universes exist in a sort of infinite Platonic realm. So, what does this mean for our quest to understand where the universe came from? In this framework, there was no need for the universe to be created at all, because mathematical structures exist timelessly. They are not invented or built, they simply are. Just like the number 7 or the ratio pi, they are eternally true, regardless of whether there are minds to perceive them. Mathematical Platonism says that our world is a concrete representation of one of these structures. It's there because it's one of the endless forms that live in this Platonic world. Imagine a library with all the possible books. Our world is just one of the books, and its own reasoning defines it completely. This view gracefully avoids the question, what made the universe? It doesn't need a reason because it's a mathematical thing and not a temporal event. A world based on math doesn't need to be caused to exist, just like the Pythagorean theorem. Critics argue that this idea is unfalsifiable and veers too far into metaphysics. After all, if everything that can be described mathematically exists, how do we know which mathematical structure is ours? Why does our consciousness perceive this particular one and not others? Some people even ask why it feels so real if the world is just math. Why do we feel love, pain, colour and time as deeply personal, emotional things, instead of as cold, impersonal rules? But supporters say that this is exactly what makes math so beautiful and mysterious. It reflects not only how the universe works from the outside, but also how perception and mind work from the inside. The Big Bounce, a universe before this one? What if the start wasn't the Big Bang? What if it was just a beat in a rhythm that never ends? What if it was a cosmic breath in a world that grows, shrinks, and bounces back? Forever. There is another thought called the Big Bounce, that the world didn't just appear out of thin air. This point of view says that our world is not the first and will not be the last. The universe doesn't have a single starting. It goes through a cycle of a big bang, expansion, collapse, a big crunch, and then a bounce into a new phase of growth. This idea might sound wild, but it has solid grounding in theoretical physics. Some models of quantum gravity, especially loop quantum gravity, suggest that space and time are not continuous but quantized, like pixels in a screen. Under extreme conditions, like those in a collapsing universe, space-time doesn't reach an infinite point of density, a singularity. Instead, quantum effects create a kind of repulsive gravity that halts the collapse and causes a bounce. You can picture a trampoline. If you softly hit it, it will bend down and then spring back up. But even if you fall very hard, it will keep pushing back harder and harder until it throws you up. In the same way, the Big Bounce works. As the universe shrinks and everything gets very dense, quantum gravity pushes back, creating a new expansion, another universe. However, there is a catch. If the universe has been moving around forever, we may never see the first universe. There might not have been a first one. This is both beautiful and confusing. The question, what caused the universe, doesn't matter in this model. The universe has always been around in some form or another, constantly expanding and contracting. This cycle might even help us figure out some of the biggest secrets in the universe. For example, the so-called flatness problem, that is, the question of why the universe looks geometrically flat, could be answered by the fact that the repeated bounces smooth out any flaws over an infinite number of cycles. The first conditions are set by each bounce, and they get more tuned with each round. What about the idea of entropy? The second rule of thermodynamics says that as something bounces, the amount of chaos should grow. Yes, unless there's a way to make entropy equal again between rounds. Some scientists think that each bounce makes the world a little bit different, maybe with a few different physical constants, rules, or structures. The Big Bounce and multiverse ideas could work together in this way, with each cycle creating a new form of reality. One of the most compelling parts of this theory is that it doesn't require a true beginning. There's no infinite regression to worry about, no singularity to resolve, no mysterious burst from absolute nothingness. It's like a pendulum, always in motion, never quite stopping. Yet challenges remain. We don't currently have definitive observational evidence of a previous cycle. Cosmic background radiation, for instance, shows no obvious signs of a bounce. However, as instruments become more precise, scientists hope to detect subtle scars or anomalies in the cosmic microwave background, echoes of a universe before ours. Could our universe be a black hole from another universe? Let us use our imaginations even more. What if the whole universe is inside a black hole? There are scientists who think this idea might be based on real science, even though it sounds like science fiction. It is thought that black holes could be like cosmic wombs, with each one birthing a new universe beyond its event horizon. Yes, this does include the black hole that may have created the universe. This thought comes from the strange way that general relativity and quantum theory work together. Einstein's theory of general relativity says that when a big star falls apart, it creates a black hole, a place where the gravity is so strong that not even light can escape. The matter falls apart toward a singularity, which is a point with an infinitely high density. But this makes things worse. When we see infinite density, it means that our models don't work anymore. Loop quantum gravity and other models of quantum gravity say that the center of a black hole might not be a singularity at all. Instead, quantum effects create a type of negative gravity at very high numbers. This is the same idea we saw in the Big Bounce. This might stop the whole thing from falling apart and instead cause it to bounce into a new place that is bigger. That is, something that looks like a black hole from the outside might actually be the start of a whole new world on the inside. The event horizon, which is usually thought of as a point where something can't be changed, could be the line between the parent and kid worlds. It's an interesting answer to a number of cosmic mysteries. As an example, black holes seem to delete data, which goes against the idea that data can never be lost. However, if the data that a black hole eats is just moved to a new world, then it might not be lost after all. Now let's take this thought one step further. What if our universe formed when a big star in a universe with more dimensions collapsed? Our Big Bang might have been what looks like a black hole in that parent universe. The growing space-time we see is actually the inside of that cosmic object. This might explain why our universe has the properties it does. If every black hole spawns a new universe, then perhaps natural selection applies to universes too. Universes that produce more black holes give rise to more offspring universes. Over time, those with physical constants favourable to black hole formation become more common, leading to universes like ours, rich with massive stars. A scientist named Lee Smolin came up with the term cosmological natural selection to describe this. It takes ideas from both astronomy and Darwinism and says that black holes might not only be the end of stars, but also the start of everything. The idea that there could be multiple worlds inside each other makes this theory even stranger. In our universe, a black hole might hold a child universe. This child universe could hold more black holes and child universes. This chain reaction could keep going forever, like Russian nesting dolls, with each level being a universe inside a universe. Brains and bulk. Did our universe collide into being? Just for a moment, let's say that our world is not the only one out there. Instead, think of it as a membrane-like structure in 3 dimensions that floats in a world with more dimensions called the mass. Now picture that there are other brains close, moving quietly. They would look like parallel sheets. What will happen if these 2 huge sheets hit each other? That's how our universe might have started according to brain-world cosmology, one of the most exciting new ideas in theoretical physics. Small strings that move are thought to be the building blocks of reality, not particles. That thought is what this theory is based on. To work right, these strings need 10 or even 11 dimensions. They don't just move in 3. In this view, the world may only be a small part of a much bigger and more complicated truth. The way this system is set up, brains are places that can be any size. Since gravity is the only force that can leak between brains, it is not as strong as the other forces. The space we live in might be a 3-dimensional brain floating in a 4-dimensional or 5-dimensional mass. For many, the Big Bang wasn't the beginning of everything, but rather the end of a big fight between 2 brains. The Epyrotic model is another name for this idea. When they hit each other hard, the moving energy turns into matter and radiation. This is what causes the Big Bang and changes the way we see space and time. After 2 worlds crashed into each other, the universe was made. It didn't just appear out of thin air. It's even more interesting that this might not be a one-time thing. Some models say that brains go back and forth between growing and merging, like a loop that never ends. With each meeting, their world starts over with a new Big Bang. Worlds are always falling into each other and making new ones. It sounds like the universe is running on a clock. This might be a way to explain the initial singularity, which is thought to be the point from which the universe apparently began to spread and became infinitely dense. In brain theory, there is no singularity. There is only a furious impact that has a limit. It also gives us a new way to think about how smooth and flat the universe is, which is another problem that inflation theory tries to fix. This isn't just imaginary eye candy, though. Scientists have been looking for gravitational waves or other signs that could be the result of a crash like this. The proof we have so far isn't clear, but the search is still going on. Some people think that in the future, tools like the Laser Interferometer Space Antenna, LISA, might be able to find waves in space-time that show we live on a brane. Epyrotic theory, a smash-bang creation. The traditional Big Bang theory says that the universe sprang into being from a point that was so thick it was hard to imagine. The Epyrotic theory, on the other hand, says that the universe began with a clash between galaxies that wasn't nothing but something that was already there. The word epyrotic comes from the Old Greek word ekpyrosis, which meant conflagration, or a great fire. This idea comes from the Stoics, who thought that fire destroyed and recreated the world over and over again. The epyrotic model in modern cosmology is based on this old idea, but changes it by looking at it through the lens of brane cosmology and string theory. Here's how it works in general. Assume two huge, three-dimensional surfaces called gigantic branes floating in a place with more dimensions, which is called the bulk. Over billions of years, these branes have been moving slowly toward each other. The stress builds until they finally hit each other, and when they hit, the energy from the crash doesn't destroy anything. It makes everything. The universe gets warmer because of that burst of energy, which creates matter, radiation, and the building blocks of galaxies. The Big Bang is not the beginning of the universe. It is the result of a cosmic crash. Scientists like Justin Curry, Bert Overut, Paul Steinhardt, and Neil Turok first came up with the idea of epyrotic in the early 2000s. The epyrotic model avoids the problems that come with standard inflationary models, which is one of its best features. In inflation, the universe grows at an exponential rate in the first few hundredths of a second after the Big Bang. This is what makes the universe look so smooth and even. It's not easy to figure out how to start or stop inflation, or how to escape eternal inflation, which creates a huge number of different worlds, some of which don't make sense. A different answer comes from epyrotic theory. It makes sense that the world we see is uniform because the branes move slowly and smoothly toward impact. In fact, this theory can make space less curved and smooth out bumps in the surface without needing an extremely fast inflationary burst. It's not a flash flood, but a slow burn. There is one more step in the epyrotic model though. The accident doesn't just happen once in some versions. It happens over and over. This leads to the idea of a circular universe, in which branes hit each other, build a universe, and then move away, only to come back and hit each other again. It's possible that each cycle will last 1 trillion years. The world we live in is just one shot in a much bigger movie. This is important for both science and philosophy. This suggests that there may not have been a first world at all, but only a never-ending pattern of death and rebirth. There is no unity and there is no infinite beginning. There is only music and repetition on a huge scale. Cosmic cycles, eternal recurrence, and the Phoenix universe. What if there was no beginning or end to the universe? What if time, matter, and life were all parts of a circle that would never end? Welcome to the idea of cosmic cycles, which say that the world is more like a phoenix, dying and rising from the ashes all the time. In astronomy, the idea of a world that will never end is not new. In ancient societies, circular time included the changing of the seasons, return, and the renewal of the universe. But now scientists are taking this idea seriously with models like the Phoenix universe and the cyclic universe. These models combine new physics with intuitions from old philosophy. Different from the epyrotic idea is the Phoenix universe. In this model, the universe grows, slows down, and finally shrinks during a stage known as the Big Crunch. But this shrinkage doesn't end in death. Instead, it leads to a bounce, which is like a new start. There is a new phase of growth and a new universe appears. Each age lasts 1 trillion years, so this loop can go on forever. The way that entropy, the idea of chaos, is handled in this case is very interesting. By the basic rules of physics, entropy always rises. This means that the world should eventually reach a cold, lifeless state called heat death. Cyclic models, on the other hand, handle entropy in a smart way during the shrinking phase. The idea is that entropy is spread out over the larger brain structure, which makes each new bounce feel like it's brand new and has low entropy again. Every time the world starts over, it's like starting over. Another very different view of time comes from cosmic cycle models. If there is no beginning or end to the world, time doesn't go in a straight line. It goes in a circle. There was no before the universe. There was only a time when the universe shrunk before it grew. And that stage came after an earlier growth. This will never end. There are big effects to this. It means that everything we experience has happened before and could happen again. Not just worlds that are like each other, but exact copies. The very same galaxies, the same people, the exact same thoughts. This concept is known as eternal recurrence. And even though it sounds like something out of science fiction, it has its roots in math, especially if there are only a certain number of possible combinations in a world. But how well do these models match up with what we see? Inflation-based models don't always agree with expectations. For instance, cyclic universes tend to suggest that certain types of gravity waves that inflation would make will not be present. We haven't seen these rising waves yet, but that doesn't mean that cycle models can't happen. Recently, scientists like Roger Penrose have put forward a different idea called Conformal cyclic cosmology, CC. In this world, each universe ends in heat death, but because matter is being diluted infinitely, time and space have no meaning. This means that the start of a new universe can start right where the end of the old one left off. Time stops changing with size. In one world, the Big Bang is the cold fade-out. Time is an emergent phenomenon. No start, no problem. What if time isn't really an important part of the universe? Would it be possible for it to come from something deeper, something even more basic than the ticking of a cosmic clock? The radical idea is that time doesn't exist in a vacuum. It's a result of rules that are much deeper than we can see. If this is true, then the question, what came before the universe, may not mean anything, since the word before doesn't mean anything until time itself exists. In our daily lives, time feels like the most real thing there is. Clocks tick, we grow older. We remember the past, but not the future. But in the world of physics, especially at the quantum level, time is slippery, more illusion than reality. Certain equations in quantum mechanics and general relativity don't actually require time to work. They describe how a system behaves as a whole, rather than how it evolves over time. The timeless wave function of the universe, described by the Wheeler-DeWitt equation, doesn't include time at all. So where does the sensation of time come from? One answer is entanglement. In quantum theory, when particles become entangled, the state of one depends on the state of another, even across vast distances. Some physicists believe this relational setup could give rise to what we experience as the arrow of time. That is, time emerges because we observe correlations between systems, like dominoes falling not because they must fall in order, but because we perceive their collapse as a sequence. Thermodynamics is another way to look at it. The reason time moves forward is often thought to be the second law, which says that entropy grows. As for the idea that entropy has been growing since the beginning of time, time might just be a way to keep track of that change. From this point of view, time is just changing, not a thing. If you take away money, time goes away. Strange things happen because of this. If time emerges, then asking what was before time is like asking what's north of the North Pole. It's the wrong category. It could also mean that there was never a first moment. Instead, there was just a change, like ice turning into water. The event we think of as the start of time could have been a change in the way the world stores information. Things were different before that, but not earlier. They were different in a way that will never change. There are also new edges here. Loop quantum gravity and some versions of the ADS-CFT correspondence are new theories in quantum gravity that say space and time come from quantum entanglement itself and are made up of a network of relationships, not places on a continuum. It's not just physics that has changed. It changes the way we see the world. What does the lack of time mean for the idea of cause and effect? What about free will? About the fact that death will happen? Do we live in a big relationship pattern where structure is all that memory and forecast are? Are we inside a computer simulation? It sounds like something out of science fiction, but what if the whole world is just a computer game? Could everything you see, feel and remember, your whole life, the stars in the sky, and even the laws of physics, come from code running on a very fast computer? This thought-provoking idea is no longer just for Hollywood. A lot of well-known scientists and thinkers have given it a lot of thought. Philosopher Nick Bostrom wrote a popular paper in 2003 in which he said at least one of the three things below must be true. It's not possible that humans will ever develop technology advanced enough to make virtual worlds. When that level is hit, people will no longer be interested in running ancestor simulators. Almost certainly, we are living in a game. The name for this is the simulation argument. It doesn't say we're in a simulation, but it makes the case that if powerful societies can and do run simulations, then it's statistically more likely that we are in a simulation than in the real world. There could be millions or even billions of fake worlds for every real one after all. But let's take a step back. What would it mean if the world were just a sim? Not like in The Matrix, where you're hooked up to a speaker. The idea is that everything in reality, particles, forces, planets, and time, is just code. A complex game that was built from the ground up by intelligent beings, which could be aliens, future humans, or even things we can't understand. Physicists have even suggested ways to test the theory. One idea is that a simulated universe might leave glitches or constraints, like the resolution of a video game. In 2012, physicists proposed that if space-time is discrete, not continuous, we might be able to detect a grid underlying the fabric of space. Others look for anomalies in cosmic rays or subtle errors in quantum entanglement that might suggest a computational origin. Some people think that the universe might not look or feel any different from the real world if it is a computer. Why should we care if the code is perfect? There's also a philosophical side to this. Does the fact that we're fake mean we're not real? Not all the time. Plan what you want. They are events, even though they aren't real. There is a chance that a virtual being can still be aware, feel things, and want things. Some people even say that awareness could be a type of computation that shows up in systems that are tough enough. There is also always the scary thought that our game could end at any time. The game could end by someone or something. There might be less chaos at the end of the world and more shutting down. However, some fight back. It doesn't look like the world was designed like software. It has messy laws, particles that are based on chance, and constants that seem strangely fine-tuned, but they are not clearly coded. Some people say that the simulation hypothesis can't be proven false, which means that it's fun to think about, but might never be tried properly. It's hard to get rid of the idea. Because computers are getting faster, we may be able to create conscious people. Is the universe a quantum error-correcting code? What if the world doesn't just follow physical laws? What if it actively protects them, like a computer program that fixes itself? That's the crazy idea behind the theory that the world works like a quantum error-correcting code, which is based on a concept from quantum computers. To put it simply, mistake correction makes sure that the general message stays the same, even if some pieces of information get lost or changed. Could it be that the world uses the same kind of logic to keep everything in order? Work in string theory and black hole physics helped spread the idea. In 2015, a surprising link was found between hologram duality and quantum error correction, two ideas that didn't seem to have anything to do with each other. For holographic duality to work, all the data in a space volume, like a black hole, must match the data on its surface. Seeing a 3D movie on a 2D screen is the same thing, but experts found that this model needs to be fixed in order to be stable. Physicists then came to a very important realization: space-time itself could be made of quantum error correcting codes, and so on. The shape of reality isn't just a physical thing, it's also a way of processing information that keeps things from going wrong. Use this as an example. Picture putting together a house of cards. One card comes loose because of a gust of wind. Normally, the whole construction would fall apart. But what if the house of cards could slightly change its shape to take the mistake into account and still stand? That is what fixing mistakes does. Now use that thought to look at the universe. Think about quantum coupling, which is when objects share information right away, even if they are light years apart. Some scientists think that entanglement is what makes space itself. However, entanglement is weak. How does the universe keep it going over such long distances and interactions? That's where quantum error correction comes in. The suggestion is that the stability of space-time depends on a built-in error correction mechanism. And remarkably, this could explain why information isn't lost in black holes, a puzzle that's haunted physicists since Stephen Hawking first proposed black holes might destroy information. But let's go deeper. What does it mean for the universe to be a code? Not metaphorically, but literally. In quantum computing, qubits, the basic units of quantum information, can exist in multiple states at once. But they're also extremely delicate, so we use error-correcting codes to store the information redundantly, protecting it from errors. If the world is like a quantum computer, then the laws of nature might be the code that controls everything. It is possible for changes to be taken in, fixed, and moved in space-time, energy, particles, or even space-time itself. This would be like fixing bugs in real time. This also makes me think that information, not just matter and energy, makes up reality. Physicist John Archibald Wheeler, who came up with the phrase "it from bit," agreed with this for a long time. This means that everything we see comes from bits of information, or yes, no questions. Even more interesting, this point of view might help bring together quantum mechanics and general relativity, which are two important parts of current physics that don't usually agree with each other. If they are both representations of a greater quantum code, then fixing mistakes could be the key to making them work together. Dreamtime realities. Consciousness as the origin. It's possible that awareness came from the world instead of the other way around. Beyond the limits of standard physics, this question leads us to one of the most interesting and old points of view. Awareness is not something that happens because of matter, it is matter itself. Dreamtime is an idea that comes from some indigenous beliefs, especially those of Aboriginal Australia. It is a timeless place where the world was thought into being. Even though these are spiritual ideas, strange similarities have been found between them and quantum physics and theoretical models. Some ways of understanding quantum physics say that awareness is a big part of collapsing the wave function, which is the cloud of possible outcomes that describes how particles act. In simple words, particles are in all possible states at the same time before they are observed. They have to choose a state because they have to measure or observe something. But if the viewer is so important, then doesn't that make knowledge the most important thing? Now think about what this means. If observation is what makes reality real, and observation requires an aware viewer, then what came first? The universe or the mind that made it possible for it to take shape? Physicist Eugene Wigner, who was one of the first people to study quantum theory, said that awareness might be a basic part of the world. He made the case that you can't have a uniform picture of reality without including the viewer. As he put it, it was not possible to fully explain the laws of quantum mechanics without taking into account consciousness. Panpsychism is the idea that the mind, in some form, is a basic fact of reality, like mass or charge. This view makes panpsychism possible. Panpsychism says that even the smallest particles may have a form of awareness. It's not that atoms and rocks think like people, but that the building blocks of experience have always been there, everywhere. There's also the idea of idealism, the philosophical stance that consciousness is all that truly exists, and everything material is simply a manifestation of mental states. In this model, space, time, and matter are emergent illusions, projections from a deeper mental substrate. Could the Big Bang have been a thought? Could space-time be a dream of something greater? It's easy to dismiss these ideas as mystical or unscientific. And yet even some of the most cutting-edge physicists admit that consciousness is the elephant in the room when it comes to understanding reality. Despite centuries of progress, science has no clear explanation for what consciousness is, where it comes from, or how it arises from inanimate matter. That leaves us with a deep mystery. Is awareness something that just appeared after 13.8 billion years of time, or was it there from the start? In a world where there is doubt, possibility, and connection, the mind may not just be a biological quirk, but a sign of something greater. The universe might not have needed to be seen to exist. It might have been there all along and been aware. The anthropic principle, we exist, therefore it does. Think of entering a room that is meticulously organized, where the temperature is just right, the furniture is to your liking, and the illumination is customized to your preferences. Think about asking yourself, why is this room set up so perfectly for me? The anthropic principle also asks that kind of question about the world. Simple but strong, the anthropic principle says that the world must be the way it is because we are here to see it. It's a statement that flips the traditional scientific perspective on its head. Normally, science aims to be objective, describing the universe without reference to us. But the anthropic principle says, not so fast. If the universe hadn't been just right, if gravity had been slightly stronger, or the nuclear forces slightly weaker, life as we know it could never have existed. We wouldn't be here to ask questions at all. Take the fundamental constants of physics, the strength of gravity, the charge of the electron, the rate at which the universe expands. Each of these values seems finely tuned. Even a small change in any one of them would lead to a lifeless cosmos. Stars wouldn't form. Chemistry wouldn't work. No planets, no people, no questions. What's going on then? Is this exact tuning just a lucky accident? The anthropic principle comes in two main forms. The weak anthropic principle just says that we can only see a world that is compatible with our own. This happens because out of all the possible worlds, we live in one that supports viewers. If it didn't, we wouldn't be here to notice. It goes even further with the strong anthropic principle. It means that the world has to have the right conditions for life to exist, not just by chance. In some ways of looking at it, this almost sounds like it has a purpose, like the universe was meant to make life. The anthropic principle is criticized for not explaining anything and stating the obvious again. This is like saying, I won the lottery because I have the winning ticket in my hand. Maybe it's true, but it's not very fulfilling. Still others defend it as a useful way to learn about fine-tuning. It helps a lot when combined with the multiverse idea, which says that our world is just one bubble in a sea of all the possible worlds. From this point of view, all the possible forms of physical rules are out there somewhere. Most of them are clean, but in some, the conditions are just right for life to start, and it's only normal that we live in one of those. The anthropic principle is also one of the few concepts that bridges physics with existential wonder. It asks not just how the universe works, but why it's so uncannily suited to us. And it invites us to think about the possibility that our existence is not incidental, but integral to the universe's story. Emergent reality, when information becomes matter. What if all the stars, particles, people, and things around you are made of information instead of stuff? The radical idea behind emergent reality is that space, time, and even matter itself aren't basic parts of the universe. Instead, they're things that appear out of a deeper, less concrete layer of reality. That layer is made up of data. Let's take a step back to see this. Picture how a high-definition video looks on your screen. The pretty, smooth pictures aren't really real in the usual sense. They're patterns that form when millions of pixels turn on and off in response to directions stored in digital bits. Physicists are now beginning to ask, what if our universe works the same way? In this view, everything we call physical, particles, forces, energy, is simply the outward appearance of something more fundamental, bits of information interacting in incredibly complex ways. This might sound like science fiction, but it's rooted in serious science. Pioneers like John Archibald Wheeler, one of the architects of modern physics, once coined the phrase "it from bit." He believed the universe is ultimately built from binary, yes-no decisions, the ones and zeros of existence. Modern physics has taken this idea further. In quantum mechanics, particles don't really exist until they're observed. Instead, they exist in a cloud of probabilities, potential realities waiting to collapse into something definite. What determines the outcome? Some physicists argue it's not energy or position or force, but information. Black holes, which are thought to be the biggest monsters in the universe, have been shown to follow rules based on information. Based on the Bekenstein-Hawking entropy equation, the amount of data, or bits, that can be held in a black hole is related to its surface area rather than its volume. This makes me think of the crazy idea that the world might be a hologram, with reality stored in 3 dimensions on a flat surface, like a cosmic hard drive. How space-time is put together could be seen through this view as a type of quantum computing. Space and time might not be basic. Instead, they may be estimates made by the universe's code. When that code gets really complicated, the illusion of consistency develops. This is what we call reality. It's not just thinking. Quantum information theory, causal set theory, and ADS-CFT duality, used in string theory, are all new ideas that help us understand that reality may not be a thing, but a process. In this case, the universe may not be a big machine, but rather a big idea. Everything from electrons to galaxies might be the result of information moving through an underlying structure, like waves in the ocean that we can't see yet. The question of creation is also changed. Maybe the world didn't start with atoms, but with the first bits, since matter and energy come from information. Not a bang, but a little. The quantum observer effect. Does observation create reality? The way we look at things doesn't change them in our daily lives. A rock will still be a rock even if you look at it all day. Quantum world, on the other hand, isn't that easy. In fact, just looking at something could make it happen. Many people are interested in the double-slit experiment, which is one of the most well-known physics tests. When electrons or photons are shot at a barrier with 2 slits, they act like waves and make a pattern on a screen behind the slits that looks like interference. It looks like each particle doesn't just go through one slit, but both, making it look like they're spread out in space. Things start to go wrong here. It's not wave-like when you put a monitor at the holes to see which one the particle actually goes through. The particle suddenly acts like a solid object and only picks one hole. The pattern of interference goes away. You've changed the system's behavior just by watching it. Why does this take place? There's no way to be sure. However, it seems that quantum systems don't really choose a state until they are tested. Until then, they are in a state of superposition, or a cloud of options. Observation doesn't just reveal reality, it may help create it. This challenges our deepest assumptions. If nothing exists in a definite state until it's observed, then what is real before observation? Is there such a thing as an unobserved universe? Some interpretations of quantum mechanics embrace this idea head-on. The Copenhagen interpretation, for example, suggests that conscious measurement collapses the wave function, meaning your act of seeing literally brings things into focus. Others, like cubism, quantum Bayesianism, go further, suggesting the wave function is not a physical object at all, but a tool for organizing personal beliefs about what one will observe. That's right. In this view, reality is subjective. Naturally, this doesn't mean that the world needs people to exist, but it does bring up some tough questions. Was the world kind of in a state of not knowing before people like us came along? Did things become clearer in reality only when something, anything, could finally see them? Some scientists say that quantum physics and the mind are closely connected. It's not that your thoughts make the universe, but that observation, in whatever form it takes, is a fundamental part of shaping what is real. This could even include the whole universe. Some ideas say that the universe may have measured itself into being in a way that makes sense on a cosmic level. Quantum events and gravity interactions may have locked in reality one step at a time. The quantum observer effect makes us rethink what we mean by reality, even if that's not true. If the world is ruled by chance and possibility, then the line between the observer and the observed might not be a wall, but a window. The holographic principle: is the universe a projection? What if everything you've ever known, your body, your thoughts, even the stars in the sky, was false? Not figuratively, but really. What if the world is like a flat surface that projects a 3D picture? That's the crazy idea behind the holographic principle, a theory that combines quantum physics, general relativity, and string theory in a way that makes no sense. It says that all the information in our three-dimensional universe is stored on a faraway two-dimensional edge, much like a hard drive in the universe. Back in the 1970s, Stephen Hawking discovered something shocking. Black holes aren't completely black. They emit radiation, what we now call Hawking radiation. But this posed a big dilemma. If black holes eventually evaporate, what happens to all the information about the things that fell into them? In physics, information must be conserved, but in Hawking's scenario, it seemed to just disappear. That contradiction became known as the black hole information paradox. Leonard Susskind, Gerard 't Hooft, and a new way of thinking about reality come along. They said that when data falls into a black hole, it doesn't disappear. Instead, it gets stored on the event horizon, which is the black hole's two-dimensional edge. This gave me a shocking thought. If all the data can be saved on a surface, then maybe everything inside the black hole is just a 3D copy of the data on the surface. Take that logic a step further and apply it to the entire universe, and you get the holographic principle. Our universe, it turns out, might be like a cosmic hologram. Just as a holographic sticker stores a three-dimensional image on a two-dimensional film using interference patterns. Our three-dimensional world could be a higher dimensional illusion built from data written on a far-off cosmic boundary, perhaps at the edge of the observable universe. String theorists and quantum gravity experts take this very seriously. It's not just academic talk. A model called ADS-CFT correspondence, which was first put forward by Juan Maldacena in 1997, is one of the most convincing pieces of proof. It proved that some types of quantum field theories working in a 2D space are mathematically the same as gravity working in a 3D space. It was like finding out that the rules for two very different games, like chess and basketball, are the same, but written in a different language. If the holographic principle is true, then the depth, distance, and even time that we think we see might just be images made from data on a flat sheet of space-time that we can't see directly. This point of view says that gravity might not be basic, but rather a result of how information is processed. It's both a very scary and a very beautiful thought. In fact, the holographic principle makes the world even more mysterious by making it seem like it works in a bigger way. It says that beyond our everyday experience, there is a world made of nothing but code and data that makes stars, galaxies, and even awareness appear out of nowhere. Are physical laws evolving universes with mutating rules? People often imagine that the laws of physics are fixed, unchanging rules that have guided the world since the beginning of time. What if they aren't carved into cosmic stone, though? What if nature's rules have changed over time? Everything we think we know about the universe is wrong with this idea. The universe may not have always been ruled by set rules. Instead, it may have gone through stages where laws were formed and physical constants and basic relationships were not always the way they are now. Part of the idea that physical rules could change comes from the fact that many of the constants in physics seem to be made just right for life. There is a small range of values for gravity, the charge of an electron, and the speed at which the universe is expanding that makes it possible for galaxies, stars, and eventually life to form. The universe might have folded in on itself or grown into a cold, dead void if any of them were a little off. The idea of fine-tuning has bothered thinkers and scientists. Lee Smolin, a theoretical physicist, came up with the novel idea of cosmological natural selection in the 1990s to explain this. It makes the case that black holes could be used to make more universes. This point of view says that every time a black hole forms, it creates a new world on the other side. It's like the universe cutting in half. The offspring universe may inherit slightly different physical constants, just like genetic mutations. Over time, universes that produce lots of black holes would become more fit and likely to survive and reproduce. This mechanism would favour the evolution of universes with parameters that naturally lead to more stars and black holes, and just by coincidence, those are the same conditions that also make life possible. So if Smolin is right, the laws of physics are not fixed edicts from a divine architect, but emergent outcomes of a cosmic evolutionary process, much like biological evolution shapes the traits of living organisms. Cosmologists like Paul Davies have wondered if the so-called constants of nature, like the speed of light, Planck's constant, and the gravity constant, have really stayed the same over time. Based on what has been seen, these numbers might change very slightly over time or place, at least in theory. If that's true, then the rules of the world are not global. They are local, temporary, or new. And in the darkest parts of theoretical physics, like string theory, there are huge areas of possible vacua, each with its own set of rules and constants. As a result, we might think that our world is just one option out of many, each with its own set of rules. Every universe starts out with a little different firmware, and the lines in the multiverse family tree that lead to stability and black hole generation are the ones that are most important. But this isn't just a thought experiment. Since physical rules can change, it's possible that the world we live in is still changing. It would mean that the universe is not a fixed thing controlled by timeless truths, but rather a living, changing thing that is growing and changing. And it might be moving toward rules that are as different from ours as ours were in the beginning of the universe. Cosmic consciousness. Hypotheses. Can awareness precede matter? What if awareness didn't come from matter? What if it came from matter into consciousness? One of the most daring and speculative ideas in all of science is that awareness might be the building blocks of reality, not something that comes from it. Not only does it question physics, but also neuroscience, logic, and the very idea of what it means to live. It is the standard materialist view that is turned on its head by the cosmic awareness theory. Both old and new theories of physics say that the world started as a chaotic explosion of energy. After billions of years of development, it led to complex structures, planets, life, and finally aware observers like us. Mind comes from matter in this story. Some scientists and philosophers, especially those who study quantum physics and consciousness together, say that awareness may be basic. In other words, awareness doesn't just show up after the Big Bang. It was there before and before it. From this point of view, the world doesn't make consciousness. It is consciousness itself, or at least, it is made of consciousness. Quantum physics is one of the main sources of ideas for this one. In quantum physics, the measurement problem is the strange fact that particles live in more than one state until they are observed. This problem makes us think deeply about the role of the observer. Some readings, like the von Neumann-Wigner interpretation, say that quantum statistics become real when a person consciously observes them. There is nothing certain that exists without a witness. If that's true, then reality isn't fully real until it's seen, which means that awareness might be built into the very rules of existence. John Archibald Wheeler, a scientist who died in 2014, came up with an interesting concept that he called the participatory anthropic principle. In his view, what he called a self-excited circuit makes the world happen in the first place. There are watchers in the universe, and their job is to keep the universe going by watching it. This means that we don't just exist in the universe needs us to exist fully. But the idea that awareness is the most important thing goes further. Panpsychism is a view in philosophy of mind that is becoming more and more common. It says that awareness is a basic property of all matter, like mass or charge. That doesn't mean rocks are thinking, but it does mean that even the smallest particles have a quality that makes them kind of aware. Particles like these can form complicated shapes, like brains, which is what we think of as having higher order perception. Maybe the world is aware in some way, either through its structure, its particles, or its quantum state. If so, then it may have come into being from a cosmic thought or purpose. Think about this. The mind is the source of all things. This is the main idea behind idealism. In this view, the world is not a machine, but a mind, which is in line with some old spiritual traditions and current speculative science. People who don't believe in this will call it nonsense, which is fair since it can't be tested like most scientific ideas can. But quantum physics has shown us over and over that our world is not what it seems to be. The role of information. Is the universe a self-organizing code? It's possible that the world is made up of bits instead of particles. A lot of scientists and cosmologists are starting to see knowledge not as something that happens in reality, but as something that reality is made of. Some people have even said that knowledge might be more basic than matter, space, or time. A scientist named John Archibald Wheeler came up with the phrase "it from bit," which helped spread the idea. In this view, every particle, field, and wave in space-time, everything we experience, is made up of bits of information that can be either yes or no. So, the world is not a machine in the usual sense. It is a code that runs itself and a computer system that changes over time. Wheeler's concept wasn't just philosophical, it was grounded in the findings of quantum mechanics. Every time we measure a quantum system, we obtain discrete outcomes: 0 or 1, spin up or spin down, yes or no. These binary interactions look remarkably like computational logic. And the more we examine the universe, the more we find that physical processes can be described as transformations of information. Information is not something passive. It can be processed, rearranged, and crucially, it persists. Black holes, for instance, led to one of the most dramatic confrontations between physics and information theory. According to Stephen Hawking's original work, black holes destroy all information that falls into them. But quantum theory insists that information must be conserved. The resulting paradox eventually led to new theories that black holes store their information on the event horizon, like a cosmic hard drive. This made it possible for the holographic principle to be proposed, which is the novel idea that everything we think of as three-dimensional space might actually be stored on a flat surface around the universe. What we think of as depth is an illusion caused by complicated rules about how information is stored and sent. So where does this leave the question? Did the universe create itself? If information is the true substrate of reality, then perhaps the universe booted itself up, like a computer running a startup sequence. And if that's the case, initial conditions weren't things at all, they were rules. Think of Conway's game of life. A simple set of rules on a grid can evolve into stunning, complex patterns, some of which even replicate themselves. No designer required, just logic. Based on this theory, the Big Bang might not have been an explosion of matter, but rather a release of information, a sudden opening up of options that had been locked away. What happened next wasn't chaos, but emergent order, which is made up of patterns that form from simple limits. If knowledge is what the world is made of, then nothingness may not have existed at all. There may have been rules, logical frameworks, or what scientist Max Tegmark calls the mathematical universe hypothesis before time. This is a place where all consistent sets of mathematical facts have the chance to be real. The universe as a computation, Pan-computationalism explored. What if the world isn't just made up of numbers and equations, but is also a kind of computation? Many years ago, a computer scientist called Konrad Zuse came up with the idea that the world works like a cellular automaton, which is like a digital grid where simple rules turn into complicated patterns. Later thinkers, such as Edward Fredkin and Stephen Wolfram, took the idea even further by saying that all of physics might have come from a computer program, like how space, time, energy, and particles are just the results of a cosmic formula. Wolfram's A New Kind of Science introduced the idea that the most fundamental rules of the universe might not be the grand equations of relativity or quantum field theory, but instead simple, recursive programs. Like Conway's game of life, these programs might start with nearly nothing, just a set of simple updating rules, and yet generate complexity without end. This view reimagines physics itself. Instead of smooth curves and continuous values, pan-computationalism imagines that everything comes in discrete steps, like pixels on a screen or bits in a program. This actually fits with some quantum theories that suggest space and time are quantized, or chopped into indivisible units. Reality might not flow, it might click. Where did the program come from? It could have been that it didn't need to be written. Pan-computationalism says that every rule that could be used exists somewhere in the huge space of mathematical possibilities. It's possible that the code that created our world was just the one that ran, like how a drop ball doesn't choose to fall, it just does. Being in this state means that creation is not about something appearing out of nothing. In a Platonic sense, it's about setting the first rules, which were rules that were always possible. The processing started and time and causality became part of the system. We can call this the Big Bang or something else. Now, some critics say this view has the same problem as the universe or simulation hypothesis, which is that it's hard to test. But it does have strong metaphors that match real-life physics ideas. Quantum computing, for example, says that reasoning, knowledge, and superposition are not just tools we use, they are real things. And the more we look, the more things in the universe that look like computers. You can think of particle interactions as being like logic switches. Black holes act like computers that store information. Even the rules of thermodynamics, like entropy and information loss, look a lot like the limits of computers. False vacuum decay. Did the universe tunnel into existence? Think of the universe as being held together by a thin thread, a layer of security that goes over a greater truth about the universe. Maybe what we think of as nothing is actually a time bomb that is about to go off. We need to look into what scientists mean by vacuum in order to understand this. Based on old ideas of science, a vacuum is just empty space. But in quantum physics, the vacuum isn't empty at all. It's a sea of energy, potential fields, and changes in energy. Space isn't just empty. It has rules, structures, and energy states. According to quantum field theory, every vacuum state corresponds to a certain energy level. The true vacuum is the lowest possible energy state, the real ground floor. But our universe may be resting in a false vacuum, a local minimum of energy rather than the absolute lowest. It's like being in a valley surrounded by hills, unaware that there's a much deeper valley over the next ridge. The scary part is that quantum physics lets tunneling happen, which is the strange way that a particle can go through a wall without going over it. In the same way, our universe could tunnel from a fake vacuum into a real vacuum, starting a destructive bubble that can't be stopped and grows at the speed of light, changing the rules of physics as it goes. We won't see this coming if it ever does happen. There would be no way to get away or warn. 1 second, everything is fine. The next, reality is ripped apart and replaced with something that has nothing to do with life, atoms, or even science as we know it. But here's where our question gets interesting. Could the universe have formed in the same way? Alexander Vilenkin is one of the scientists who thinks that our universe might have tunneled into being from a quantum void that was already there. From this point of view, nothing wasn't really nothing. It was a high-energy fake vacuum state. The universe started out as a bubble of lower energy that grew very quickly through inflation. This thought fits well with the idea of quantum creation from nothing, but in this case, nothing was a very powerful quantum field. It suggests that the universe may not have had to be created in the traditional sense at all. Instead, it could have emerged as a spontaneous transition from one vacuum state to another, a cosmic phase shift, like water freezing into ice. No God, no designer, just the natural result of quantum instability. That brings up another question though. Where did the false space come from? And this is where science starts to get rough. Our universe may have had its own past and rules before it came into being, or it may be just one of many in a multiverse with rules we don't fully understand yet. But the main idea is still the same. Our universe may have formed from a fake void through quantum tunneling, without the need for an outside force. It might not be safe. The change might not last. But for now, it's ours. Cronon theory. Are time and space made of discrete units? When we look at a ticking clock, it feels like time flows continuously, a smooth river, endlessly gliding forward. But what if this flow is an illusion? What if time itself is made of tiny, indivisible chunks, much like matter is made of atoms? Enter Cronon theory, a speculative yet fascinating idea that suggests time is not continuous. It's quantized, meaning it advances in discrete units, called chronons. These would be the smallest possible increments of time, a Planck time of sorts. Just as a digital image is made of pixels, the universe might be composed of tiny moments stitched together to form the illusion of motion, change, and causality. A basic idea in both classical physics and general relativity that Cronon theory questions is the idea that space and time are smooth, continuous materials. Einstein thought that time could bend, stretch, and twist, but it never skipped or jumped. That's not true according to Cronon theory. In this view, there is no change in reality between chronons. They are the tiniest ticks of the universal clock, and nothing happens. If there are chronons, then motion is not always going on. A particle wouldn't move from one place to another slowly. Instead, it would jump from one place to another every time the global clock struck 12. Planck time is about 5.39 times 10 to the negative 44 seconds, so the gaps between them are so small that you wouldn't even notice the jumps. That's about the same as 1 second being equal to the square of the age of the world. But why does this matter when we ask if the universe created itself? Because if time is quantized, it suggests that the beginning of the universe wasn't a singular moment, but the first tick, the first chronon. That would mean the universe did not emerge within time, but with time. There is no before the first chronon, because before has no meaning when time hasn't started ticking. This provides an elegant resolution to the age-old question, what was before the Big Bang? If chronons are real, then there was no before. The first chronon is the origin of time itself. It's also possible that space could be divided or broken up into voxels of volume that can't be separated. All of this together points to a digital universe, a world made up of countable basic units instead of smooth, continuous lines. This seems to fit a lot with new ideas like loop quantum gravity, causal set theory, and even digital physics, which all say that the universe might be like a big computer program or code in the end. What if the universe didn't need a maker or a main force? It might be able to make itself with just cause and effect, plus quantized spacetime, as its rules. It's possible that the universe is moving forward frame by frame, like a cosmic picture reel. This could explain the illusion of a continuous timeline, the growth of space, and even the birth of particles. Hyperuniverses. Did our universe split from a higher dimensional realm? What if the whole world, with all its galaxies, stars, and atoms, was just a ripple? A droplet that fell from something much bigger, something we can't see, touch, or measure, because it's not in our world? This is the big idea behind the hyperuniverse theory. Our universe might have split off from a bigger, higher dimensional world that is sometimes called a hyperspace or hypercosmos. It would mean that the Big Bang wasn't the start of everything. It was just the birth of our little bubble, removed from a much bigger structure that we can't even begin to picture. We need to think outside the box to understand the idea of a hyperuniverse. There are 4 dimensions in our universe. 3 of them are space and 1 is time. String theory and M theory, on the other hand, say that reality might have 10 or 11 dimensions. We can't see most of these because they are curled up at the quantum level. But what if they're not just mistakes in the math? What if there are higher dimensional worlds and we are just a flat sheet, a brain, floating in a huge space with many dimensions? The Big Bang wasn't the beginning of time or space in this view. It was a local event, a kind of spatial split, or a clash between brains. For a moment, nothing. The next thing that happens is that a part of the hypercosmos that was pinched off grows, like a bubble. That balloon is the whole world. Think about blowing a bubble into a pool. What's in the water is the hyperuniverse. Our universe is the bubble. You can't see the pool from inside the bubble, but you came from the pool. There is something bigger going on than nothing that you can't even begin to understand. This idea is based on a number of different theories. According to brain cosmology, our world is just one of many brains floating in a bigger bulk of higher dimensions. This is especially true for Epyrotic models. Brains sometimes bump into each other, and the energy from that impact creates a new universe, or Big Bang. Since these crashes can happen over and over, new worlds can be created over and over. This view changes how we think about how the world was made. You don't have nothing from nothing, you have something from something bigger, like a branching, cascading reality, where worlds split, join, crash into each other, or peel off of hyperstructures. Because light, gravity, and mass are only in our brain, we wouldn't know. But there might be gravitational echoes, anomalies in space that can't be explained, that point to faraway brains interacting through the bulk of higher dimensions. If our universe did split off from a hyper-universe, it might also explain a big mystery. Why does the universe seem to be just right for life? It's possible that the conditions, dimensional rules and physical constants that universes get from their parent structure are passed on to the new ones. And only a few of the bubbles that form are set up in a way that makes them complicated. That's just how it is with ours. Even crazier? The hyper-universe might not just be a background, it might actually be living. Changing shape and birthing new worlds in response to chaos, like how a stormy sea throws up bubbles that become islands of reality. We may never be able to directly observe the hypercosmos, but it's becoming a real contender in the discussion of cosmology in terms of math and ideas. And if it's true, then the beginning of the universe wasn't a pointless void. Why we may never observe the first cause, and why that matters. When there are no more ideas, models, or philosophical maybes, the last and most sobering thought is, what if we'll never know? We can't know what the first cause was, not because we haven't tried hard enough, but because we don't know what it was. This isn't an easy way out. It means recognizing the boundaries of what can be seen and what can be inferred about causes in a universe that may not be open to its own beginning. It's possible that we will never be able to see, test, or measure the answer to how the world started. Why? The edge of space. Because of the Big Bang, light has only had time to reach us so far. That's 46 billion light years in all directions. But what else? There has never been any news. It is not possible to directly see the beginning of the world, if there even is one. The moment itself is not what we're looking at. Then there's the matter of quantum uncertainty. Things that happen in space and time start to mix together at the smaller sizes. In the traditional sense, there is no cause if the world came into being from a quantum fluctuation. Instead, there is a range of probabilities that come together to form one result. The only thing that matters is that it did happen. Even worse, time itself may not be fundamental. If time is an emergent property, then the notion of a before the universe is meaningless. You can't ask what happened before time any more than you can ask what's north of the North Pole. The question breaks down under its own assumptions. But perhaps the biggest challenge is epistemological. Any explanation we devise, whether mathematical, philosophical, or speculative, is built from inside the system we're trying to explain. We are creatures of this universe, with brains wired by its physical rules, observing it with tools made from its particles, shaped by its laws. Asking us to understand what created the universe is like asking a video game character to understand the device it's running on. And yet, the absence of certainty is not the absence of meaning. Quite the opposite. That we may never truly see the first cause doesn't render the question pointless. It elevates it. It transforms our pursuit of cosmic origins into something grander than discovery, into wonder. Throughout history, boundaries of knowledge have always seemed insurmountable, until they weren't. We thought the Earth was the center. We thought the stars were fixed. We thought time was absolute. And each time, we reached beyond. So perhaps the first cause isn't invisible, just obscured, waiting for a better telescope, a new equation, or a revolution in understanding. Or maybe it's woven into the background noise of the cosmos, a subtle signature waiting to be decoded. And so we end not with an answer, but with a horizon, a place our minds stretch toward. Because whether it came from nothing, from another universe, from a code, a fluctuation, or some deeper strangeness, the fact that we exist to ask at all, that we wonder, we seek, we reach, is a miracle in itself. In the end, maybe the most haunting truth is this: we may never observe the first cause, not because it didn't happen, but because we're trapped inside the story it began. Whether the universe bubbled into being from quantum foam, spun into reality from brains colliding, or coded itself into existence through pure information, one thing remains clear. The more we understand, the more the mystery deepens. So if you enjoyed this journey through cosmic origins, make sure to like, subscribe, and tap the bell, because in upcoming videos we'll explore where time might end, what happens after the universe dies, and why your very existence may be the key to unlocking it all.